Okay, so let's convert this into something usable. Let's convert this into the form that we know as the hyperbolic ligand binding equation. And so if we look, this all originates from the law of mass action. So Kd equals PEQ times LEQ over the protein ligand complex equilibrium concentration. And so we know that theta is equal, we're going to define theta as the concentration of the ligand protein complex at equilibrium over the total protein concentration, P naught. Okay? And so that means what we want to have is we want to keep this within the equation. All right, so this needs to remain, which means we don't want to substitute anything in for it. So we want to substitute other parts, either P equilibrium or L equilibrium, into terms of PLEQ. So we can do that, for instance, from equation A, shown here. We can rearrange this by subtraction, where P naught P equilibrium is equal to P naught minus PLEQ. Okay? And so this allows us to substitute PEQ here into something that has a unit which is initial protein concentration, which again we can control experimentally. We know what this is starting at the beginning experiment, and then convert into something that has units of PLEQ. So that remains within this. So that's one substitution that we make, and I'll show you the effect of that in a second. We also make a second substitution, and this has to do with the assumption that's important for making this mathematical model more simple for us to use. And so if you recall from the last video, we said that P naught was going to be equal to 5 micromolar, and L naught was going to be equal to 10, I believe 5, 10, 15, or 20 millimolar. So these are all 1,000 times higher in concentration than the protein concentration. What we have here is we have a limit that allows us to make an assumption. What that means is, what happens in this case is that even if all of the protein had ligand bound to it, so 100% of the protein had ligand bound to it, that would decrease the ligand concentration only by 5 micromolar. Now 5 micromolar from something like 10 micromolar ligand is a big difference. You've now bound about half of the ligand in the solution. But compared to millimolar concentrations, again, these are 1,000-fold larger, it's a very small difference. And so what we do is we assume then that the concentration of the ligand doesn't change over the course of the experiment. So starting from the initial to equilibrium, the ligand concentration doesn't change because the protein concentration is so small. So we can say when ligand concentration is much greater than the protein concentration, the initial protein concentration, we can actually cross out the term in this ligand. And so ligand naught is equal to ligand at equilibrium because the change in concentration is so small. And now we can use that and we can substitute in here for something, again, that we know that we've added to the experiment. We can control for this ourselves. So this rearranges this equation to one that looks like this. So again, we substitute the protein concentration, the free protein concentration at equilibrium. So that goes in here. P naught minus PLEQ, okay, over PLEQ, and then this is ligand naught. So now we have a bunch of terms. We have PLEQ, which we're going to solve for algebraically, and then we have P naught and L naught that we can control for in our experiment. And by rearranging this equation so that we solve for PLEQ, what we end up with is an equation that looks like this. PLEQ equals, let me just make sure I have this written down. Oh, I have that written down in the wrong place. So that's going to be PLKD plus L. Oh yeah, of course. P naught L naught over L naught plus KD. Okay? And then when you divide both sides by the initial concentration of the protein, what you get is this cancels out. This becomes P naught. And you get the final form of the equation because we know we have defined the concentration of the ligand-protein complex at equilibrium over the initial protein concentration as theta. And we get the final form of the equation as we've seen it before.